C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovid's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
Alrighty, good day, folks. Welcome to our webinar. We're going to get started here in about a minute or so. Just wanted to make a couple housekeeping item announcements. Today's session will be recorded and available for playback at the end of the webinar. If for some reason you have to jump off, or maybe you have some colleagues that weren't able to make the live session, you'll be able to catch up on everything that was discussed after the fact. I'll also make note of the Q&A feature. So for those that, if you wanted to, ask any questions or basically bring anything in terms of application, examples that are shared, or just maybe some stuff that you're working on, please feel free to make use of the Q&A feature. We'll go through a dedicated Q&A kind of session with folks towards the end of the presentation. All right. That being said, I know we're a few minutes past the top of the hour, so we'll go ahead and jump into it. So once again, welcome. My name is Arya Hakimian from C-Therm Technologies. Today, our topic, webinar titled Winning the Heat, the Race Between Electronics and Thermal Materials. Very excited that I will be joined by Michael Strong, head of R&D at MG Chemicals. So he'll be joining us in a few minutes after a brief introduction to take us through some nice content here today. But before we get to the star of the show today, I will just do a quick little introduction for those that may be new to C-Therm, who we are and what we do. So C-Therm Technologies, we are a company that focuses on the measurement of thermal conductivity, specifically leading the transient class of measurement technique, which will be what is, of course, heavily featured in today's session. So our core instrument platform is called Trident. You can see a picture of this on screen here. Trident is developed as a modular platform. So it brings together multiple methods for thermal conductivity characterization. There are certainly scenarios where there may be one or more methods that can solve the task at hand. But ultimately, with the wide variety of materials and testing conditions that exist, there is often the need to apply a multi-method approach. And what we've really tried to advocate here for on the Trident platform is giving you the option to pick and choose the best tool for the task at hand. A lot of the embodiment of this idea can be summed up by this quote from Abraham Maslow. It's one that we like to reference back to: when all you have is a hammer, everything looks like a nail. So again, where we see a lot of issues come up, especially for folks that are dealing with a wide variety of either material formats, solids, liquids, powders, paste, low, high K materials, trying to take one method of measurement and broadly apply it can be challenging. So again, being able to pick and choose the best approach to get the best possible data. This is just a very quick high-level overview of some of the different methods on the platform. I won't read out every single specification here, but ultimately the Trident platform brings together a variety of approaches, some being more, let's say, calibrated and automated, like the MTPS. Others, though, require more operator input, some more user oversight in the test, but they all, of course, again, have their place, whether it's related to the temperature range you're looking to test under, the sample type, the specific standard that you are looking to conform to. Again, this can somewhat dictate the best approach. But for today's talk, and a little bit of what Michael will be discussing here, I wanted to just quickly give a quick recap on transient, how the measurement works, and then highlight one of the methods in particular. So for those that may be new to thermal conductivity, generally speaking, we can group measurement techniques into two main categories: either steady state or transient. So again, we focus on the transient class of technique. And the idea here, fundamentally throughout all the different methods, is that the sensor itself is acting as our heat source. So this is placed in contact with your material of interest. We are subjecting this sample to a thermal input generated from this sensor itself and monitoring that temperature change as a function of time. And with any transient technique, part of the reason it gets its name is that we are doing the analysis and, determining the thermal conductivity during the region in which temperature is essentially changing as a function of time. It's not entered into that, steady state condition. So one of the nice benefits, just, fundamentally based on this alone, is that all transient techniques will always be simply much faster than steady state, based on how the actual measurement is approached. Now, of course, each specific option does have its own unique set of considerations and things to keep in mind. So with that being said, I just wanted to discuss a little bit on the transient plane source, or TPS method. So the TPS, you can see here, some things I always like to point out. It's a very thin, flexible, double-sided sensor design. It is one that I think we kind of saw in that table earlier, conforms to the ISO 22007-2 standard. That is one that we do see referenced quite a bit on technical data sheets for things like thermal interface materials, a variety of polymer-based samples. So really good, really nice fit there. In terms of what's actually going on with the TPS during the measurement, where it's double-sided in its standard mode of operation, you're always going to need two samples. So one sample on the top and bottom. This essentially creates that stack around the sensor. Now, with the TPS, this is one that does require the operator to essentially input your measurement parameters, those being primarily the time and the power setting. There's also some different sensor sizes like you saw from the image previously. But basically, you'll set up your experiment. We collect, again, that delta T as a function of time. But then there is a verification process, essentially, that the operator will run through. There's a series of checks that need to be met. These are all stemming from guidance provided in the ISO standard. But ultimately, the user is full control of your test parameter and measurement design. But with that control over the setup comes the responsibility in terms of verifying the results, ensuring conformity with those various ISO requirement checks. So, I'll leave it there. We could go into further detail on the different checks and what that is. But I just wanted to quickly introduce the method, and again, kind of set up for some future discussion going forward there. The last thing I'll kind of highlight is with the TPS, always good to talk about, what are the sample size requirements? What types of materials is it really designed for? And with the TPS, we break down the functionality into different utilities, or you can view these as modules or modes of operation. Your bulk utility is really your most simplistic form of TPS testing, really geared towards isotropic materials. And the big thing I'll just flag is the sample size requirements here. For the TPS method, sample size is dictated based on the sensor size that is used. So you can see here quite simply the diameter of your test sample has to be 2.5 times the diameter of the sensor that is chosen, with a thickness scaling 1 to 1. And again, double-sided sensor, so you would have to have these produced in duplicate. I will also just mention that with the TPS, it does open up the door for some unique sample testing in terms of materials that are, thin film formats, slabs, which are typically a higher conductivity, thinner sheet-like samples, and also anisotropic materials. So there is quite a range, I would say, in how in depth you want to go. If it's just, again, more bulk material testing or some more novel sample formats, the TPS does provide some nice options in a variety of contexts here. So all that said, I will just make note that we do have a method selection guide available as a free resource download on our website. My colleague Angad, who's moderating the session, may also be putting in some links into the chat as we go here today. I will just mention that this was recently updated. It has a lot of information on all of the methods available on Trident, as well as other options that exist in the industry. So whether you're new to thermal conductivity or you're just looking for maybe a refresher on what's kind of going on in the space, this is a great resource to take a look at. Lastly, I will also just flag that, while C-Therm is focused on thermal conductivity, we also represent Rigaku as well as Metrovib in North America for their line of thermal analysis and dynamic mechanical analysis, respectively. So if you did have questions or were interested in other material property characterization, we'd be certainly happy to assist there. Also, Thermal Analysis Labs, TAL, is a full-service contract testing division at C-Therm. So they're our testing wing. They have all of the methods that we offer through Trident, as well as other options in industry as well. So if you were looking for contract testing services in support of your research, again, also happy to have those discussions. And I'll end here with a little testimonial. We always like to reference back what our clients are saying about us, their experiences with working with us, etc. So I chose this one. This was from National Research Council of Canada, Nina Ravandi, who's a technical officer. Overall, I've found the C-Therm's Trident thermal conductivity measurement system to be reliable and user-friendly. Its performance has been efficient in delivering accurate and consistent results. So we do have a full list of client testimonials available on our website. If you wanted to check out what other folks had to say about their experience with us, certainly feel free to check that out. But that being said, that brings me to the end of the little introduction here. At this point, it is my pleasure to introduce you to Michael, who will be taking us through the bulk of today's session. So thank you very much, Michael.
Okay, and thank you for that introduction. I'm going to start with a screen share. Okay. Excellent. Okay, and to start, we'd like to say thank you to C-Therm. We had the opportunity to do a presentation with them last year, so we are thankful for an invite back. We always appreciate the opportunity to reach out and share what we do with new audiences. So thanks again. Today's title is Winning the Hate, the Race Between Electronics and Thermal Materials. So what I want to do today is look at some of the different thermal interface materials, and we look at basically some of the features and benefits. So there is no best solution that's a catch-all for everything. There is differences amongst the different materials. So I sort of highlight that along with what type of applications these are used for. And hopefully that gives you an appreciation and a bit better understanding of why we've come up with the different thermal interface materials. Now, to start, I want to talk just briefly about MG Chemicals. We are now celebrating our 70th year in operations, but we come from very humble beginnings. In fact, it was a couple out in Western Canada who owned a radio and TV repair shop. And MG Chemicals was spawned out of frustration from one of their suppliers who was a bit late in delivering some of the contact cleaners. So they said, well, why don't we just develop our own? And that was the foundation of MG Chemicals. It was purchased by the Clark family in the late 1970s, in which it still remains, and we have since expanded off of just tabletop cleaners to now materials that fully service the printed circuit board. So that is coatings, greases, adhesives, protective resins. We are located in Burlington, Ontario, which is about 40 minutes west of Toronto. We have an international hub of distributors, which is our primary sales channel. We design and manufacture and, in fact, stock all of our products here in Burlington, including a state-of-the-art research lab where I myself started and have firsthand experience so I can talk about a lot of these materials that we're going to discuss today. Okay, so on today's agenda, we start with the need for thermally conductive materials in electronics. And there I kind of walk you through a timeline of the last 40 plus years in how electronic innovation is what's driving the need for thermal interface materials. Essentially, our electronics can compute more, they use up more energy, they thus produce more heat, and we've got to figure out ways to cool our devices so they continue to work. From there, I look at different thermally conductive compounds, starting with potting, moving to greases, gap fillers, gels, and adhesives. And there I sort of walk through what are some of the key features of these different types of products, as well as what our customers are using these for. And hopefully by that, you can get an appreciation of why we've come out with different interface materials. And then finally, I talk briefly about some of the measurement techniques that are familiar to us. So it's very much an introduction in terms of the theoretical aspects and how these work. Ari had talked about TPS in his introduction, so I don't really need to go over that again. This is more from a user's perspective and just to compare and contrast our experience, because here we're chemists, so it's more about getting results quickly and reliably so that we can tweak our formulations accordingly. Okay, so what drives the need for better thermally conductive materials? And here I've provided a milestone chart going back to the 1980s. And one of my thesis was, okay, well, essentially what dictates the amount of heat that's going to be generated out of an electronic, and it's the amount of power. Well, for a lot of our electronics that have been computerized throughout the decade, that is going to be governed fundamentally by the processor speed. And so we see in the 1980s, we're dealing with 6 to 10 megahertz, and these are for typical home computing devices, maxing out at about 33 megahertz for the Intel 8386. That was in 1989, so the latter end of the decade. And in terms of my research, I could not find any evidence of a commercial thermally conductive material. That doesn't mean it doesn't exist, but within the scope of what I was able to find, well, I couldn't find evidence that these were really on the market. So what you had essentially was polymer materials. And I can tell you right off the bat from doing enough measurement that an unfilled polymer material is going to give you 0.2 to 0.3 watts per meter Kelvin. Watts per meter Kelvin is a standardized measurement for thermal conductivity. And the higher that is, the more heat essentially is able to dissipate from one surface to the other. So if we move now to the 1990s, we get a jump of about an order of magnitude to anywhere from 60 to 500 megahertz. So now we're in the age of the internet. We have to download web pages as we browse. Computer games have better graphics, better rendering, lower latency. And we do start to see that thermally conductive materials, specifically adhesives, come to market. Now, these measure between 1 and 3 watts per meter Kelvin, and I can tell you that that is still a competitive number for today. If you've made something in that range, you've done a decent job. The issue is this is restricted to what at least I could find to silver-filled materials. And these have a couple constraints. One, they are quite pricey because silver is not a material that they just give away. And the other is that silver is electrically conductive, in which case you have to be very careful about where it's applied because these can cause electrical shorting if they're not localized. Moving into the 2000s, again, we see another jump at about an order of magnitude. Now we're into the gigahertz range of processor speeds because we have streaming. Games are just much more advanced in terms of their graphics and their renderings. We don't really see a shift in terms of performance, at least not what I could find, in terms of TC materials. Now we do see the introduction of more, but if we just stick to thermally conductive adhesives, at least the ones on the market, about the same performance when we look at the thermal conductivity in that 1 to 3 watt per meter Kelvin range. But now we've started to look at new materials in which to fill these adhesives with. And so we switched from silver to materials like alumina, aluminum nitride, boron nitride. And these are advantageous in a couple of ways. One, they are not quite as expensive. And two, they are not electrically conductive. So now we circumvent the issue of potentially shorting out our materials. And now moving ahead to the 2010s, we see another jump slightly in terms of processor speed, but we see, I don't want to say an explosion, but we see an increase in thermal conductivity and really the subject of thermal management altogether. We now start to see trade shows dedicated strictly to thermal management and it becoming more of a talking point with chemical companies and a meaningful part of their product offerings now is in TIMs and thermally conductive materials. And we see a subsequent jump from about 1 to 3 to now anywhere from 1 to 10 watts per meter Kelvin. And a lot of that was in the space of gap fillers and sort of thermal gels, not so much adhesives, but the performance of adhesives overall increased as well. So again, essentially what's happening here is computing speed is getting faster, producing more heat, and that's driving the innovation in the thermally conductive material space. So starting with thermally conductive potting compounds, this is probably the hardest assignment for a chemical formulator because it's a balancing act. So for those that are unfamiliar, a potting compound is a resin material that has to be sufficiently low in viscosity, flowable enough that it can wet out a surface area or fill a volume. And the difficulty here is that when you take a polymer material, which again is liquid, and start to fill it with thermally conductive materials, those fillers start to absorb oil. And as a consequence, your viscosity is going to increase. Now, there are tricks that you can use, additives that you can use to increase the filler ratio and try and control the viscosity, but it does have its ceiling. So here you're very much a balancing act. And as a result, you basically are limited in how high of thermal conductivity you can achieve. As of the technology we have right now, I would say that is about 1 to 1.5 watts per meter Kelvin, where you're still getting, it's usually a pretty thick material, but it still has enough flow to fill a volume, which is its main objective. So again, if you have less flow sag, it typically means you've added more fillers, so you achieve a higher thermal conductivity. But your flow, your ability to wet smaller components, or just to pump the material using automated equipment is compromised. And the other thing you got to be careful of is the type of filler you use itself. Some of these fillers, the morphology is very jagged and sharp, and some of the equipment guys aren't very keen on that because that'll scratch and tear up their dispensing lines. So there's a lot of give and take when making a thermally conductive potting compound. Better flow means you've probably lowered the thermal conductivity filler, so subsequently the thermal conductivity isn't as high, but you've prioritized flowability in that sense. So where do we see this in use? And typically we see a lot for motors and inductors. So remember that these are electrically insulating or non-conductive materials, so they can be applied directly over conductors. And motors and inductors generate a lot of heat as an output. So we see a lot of our customers use a thermally conductive potting compound. So the two main advantages you see if you look at the chart on the lower right-hand side, when you increase thermal conductivity, you not only lower the temperature rise, but the time to reach a thermal equilibrium. Okay, so now moving on to thermally conductive greases. This is, by contrast, a much easier assignment for a chemical formulator. Some of you may have attended the webinar I did last year where I talked briefly about how to formulate a grease, but it's actually quite simple. You start out with a base oil, which could either be a silicone oil or a synthetic oil, and you simply add your fillers and mix and disperse it. These fillers absorb the oils, and so you move from a liquid to a paste material. And so because of this, you're not really worried about how the material flows. It does not have the objective of being able to flow and fill a volume. Most of that is going to be worked either manually or through compression when you squish down on the grease to spread it out. So in that sense, you can add a lot more filler to achieve your thermal conductivity goals. The aim is to make it what's called thixotropic, which just means that you have thinning of the material with a shearing force. So the best way to think about that is if we pack it into a syringe and we have a plunger on the back, we are shearing it as we push it out of the syringe. But then if we were to put it onto a wall, a vertical wall, the material regains its initial viscosity. It's quite thick, so it doesn't flow and come off of the wall. Couple points that I have to iterate though, and I can say this firsthand, having done quite a bit of technical support. A grease is not a material that cures. It remains a paste, so it is not undergoing any kind of chemical change. It does not polymerize in any way. It can be applied, and then you can fire up your materials as you want to. It can only be used in localized spots because it will not fill a volume. So in the picture on the left, we see somebody manually sort of troweling it to a smooth consistency to make sure it covers the entire surface area, which is something very critical with thermally conductive applications. Now, the downside is it can dry out over time depending on how it is exposed to higher temperatures, because again, this is a dispersion of oil and filler. And what happens is with high temperatures, you could be evaporating that oil out over time. And then what happens is the grease tends to dry out and chalk. And then there's nothing really holding that filler together in any kind of array, so you actually lose performance. And that has come up with some major equipment suppliers having used we'll call it a cheap thermally conductive grease that is dried out and essentially caused overheating in some expensive hardware. So it's very important that you do the work necessary to ensure that you have the right material and that your grease is not going to fail you. When do we see usage for thermally conductive grease? Well, the big thing is with computers and gaming consoles. Again, we've seen such an improvement in terms of graphics, latency, rendering, and this does cost you a lot of energy. So subsequently, that energy is converted to heat, and you've got to help it escape through heat spreaders. Otherwise, we have problems with our graphics cards, our CPUs. So it's an interface material that is applied typically over the CPU, and then you will compress it thin with the heat spreader. Now, it's not an adhesive. It has no holding power, so the heat spreader must be secured with typical fasteners, and for the most part, that's screwed in. The other point I should mention, and this will apply to other materials, is that grease is reworkable. And that just means you can easily clean and remove it from a surface. It's not there permanently. It's a temporary material. If need be, simply remove the heat spreader, wipe it with a bit of alcohol, and all the residues are gone. Next, I want to look at two materials, gap fillers and thermal gels. So we'll start with the thermal gel because it's very much like a thermal grease or paste. It has a similar consistency, but if you can imagine putting your finger in grease, as you take it away, you'll notice you have sort of an oily residue on your finger, whereas with the thermal gel, that's not really the case. It doesn't really transfer that kind of greasy feel or residue to you. And one of the highlights of these products is that you can achieve a very thin bond line. So bond line thickness is very critical with thermal interface applications, and it gets a bit overshadowed when we just talk about thermal conductivity. So thermal conductivity is an intrinsic property, and it's a very important property, but one of the other things that's lost is thermal resistance. So if I put down a high TC material, but I can only put it down very thick, that in fact might inhibit the flow of heat, because what I want to do, aside from getting good surface area coverage, is compress it very, very thin, and that lowers my thermal resistance, so the heat can transfer from one material to the other and out away from the circuit board. So with thermal gels, we can actually achieve bond lines as low as 25 microns. So that's pretty remarkable. The other thing, of course, is that these are flame retardant, meaning if they were to catch fire, they self-extinguish. This is not a feature that you would have with a grease. If it were to catch fire, it'll simply burn, separate out the oil, and continue to burn. Now, silicone gap filler is a little different in that the materials we've talked about, the thermal gels and thermal grease, these don't cure. They're one part, you apply them, and then they're on. A silicone gap filler is a two-part material that actually does undergo a chemical reaction. And its main advantage is this: as it starts to cure, the material will actually expand. And that's important because even though if we were to look at the surface of a CPU and the bottom of a heat spreader, we would think that they're very flat, they're very pristine, high precision machines so that they sit flush with one another. And in fact, that's not the case. If we look at it from a microscopic perspective, these have a lot of irregularities, and those irregularities are where we can have air pockets. And those air pockets would act as thermal insulators. So what the silicone gap filler does is because it expands, it takes the path of least resistance and it actually fills in those gaps. So it's a very conformal material. It's also very low modulus, so you can compress it quite thin, usually between 50 and 100 microns, so you get fairly low thermal resistance. And again, like the thermal gels, this is a flame retardant material. And then the last material is thermal pads. Thermal pads are not chemical products. They're simply fabric type materials with thermal filler embedded in them. They are good materials. They achieve very good thermal conductivity. The only issue, of course, is that you've really got to be good with how much you can press the heat sink with the CPU. And that's to get a more conformal contact between the two surfaces. You do run the risk, however, of having a slight air gap. So again, like the other materials, this is flame retardant. So when would we see use of a gap filler or a gel? And you can actually use them interchangeably with a grease. So PCs, gaming consoles, we don't really see them within the hobbyist market, though. I think just the more technical products tend to scare people away, whereas a grease is something that is very low risk. It's not a storage hazard or anything like that. So I think people prefer thermal greases in that respect. But remember, these are not only flame retardant, but they don't dry out. So they're more suited. I mean, you could use them interchangeably with the grease, but they are more suited for harsh environments because here, once you apply them, you really don't have to worry about the oil separating out like with a grease. For a lot of our customers, they'll ask us, how long does it last for? And that's going to be contingent on the temperatures it's exposed to. So we usually recommend preventative maintenance schedules of 6 to 12 months just to go in and check. Sometimes they can do that, sometimes they can't. So in which case you might want to consider a thermal gel or a gap filler instead. But these do also see a lot of use in data intensive infrastructure such as telecommunications or even LED lighting because these things get quite hot. They're low modulus, which is just a fancy way of saying they're very soft, and that we understood because they can be compressed so thin. So they do handle aggressive thermal cycling very well. And so they will see use as well within aerospace because, as you can imagine, a plane flying at altitude experiences temperatures of minus 30, minus 40, but in certain areas on the tarmac, I'm sure it can get up to 60, 70 degrees Celsius. So that big temperature swing comes with a lot of expansion, contraction of the material. But if it's very soft, it's not stressing the components that it's interfaced between. Okay, last one we want to look at is thermally conductive adhesives. And again, as far as my research could tell, these were one of the first types of TC materials on the market. Initially coming out as a silver-filled system, which, as we discussed, has its drawbacks, have since been switched to electrically insulating fillers like boron nitride, zinc borate, alumina. It's important to note too that a lot of these systems incorporate multiple filler types because they do work synergistically. It's not as if just adding one material that has good thermal conductivity tends to do it. And what a lot of strategy now revolves around is changing the size and morphology to limit the dead space because these are dispersions, they're amorphous, they don't have any structure. So the idea is to pack the fillers as best we can into these polymer matrices. Now, important is that these are considered permanent materials. These provide not only thermal conductivity, but structural holds, so they do not need fasteners or screws like most other materials. And so we will see them used not only in heat sink bonding, but thermocouples as well, where the thermocouple might be mounted to the wall of something that needs to stay vertically aligned. You can use a thermally conductive adhesive. And typically, not all the time, but oftentimes these are flame retardant as well. So that's just another advantage. So where do we see application of this? There's a lot of automotive application calling for thermally conductive adhesives. The EV battery is a good example because these things get very, very hot. So it's used to laminate cells within a battery pack. And what that does is it helps transfer the heat laterally so that it's moving in a direction and geared towards the sort of chassis of the battery pack to help dissipate the heat. As well, again, as I said before, a lot of these materials are flame retardant, which creates fire barriers. And one of the risks for these battery packs is them catching fire. So that's an added benefit you get with an adhesive material compared to something like a grease. In traditional cars, we see the computerization for a lot of these systems. So some of the more data intensive systems that would generate a lot of energy or use a lot of energy, I should say, will use a thermally conductive adhesives, such as the advanced driver assistance system. Okay, so that covers the different materials, and I want to just briefly go over two of the transient methods that we have used at MG Chemicals. So this is not so much a technical perspective, but more just a user's perspective in terms of how the instruments have helped us and just sort of a compare and contrast. So to start for the first, or so I should say for the last 15 years, we had been using an instrument called an LFA or laser flash analysis. This technique is about 60 years old. And the basic premise can be seen on the left. We have a sample, which is typically a disc. It's held in a thermal equilibrium. And then once it's reached equilibrium, you hit it with a laser pulse. And then what it's doing is it is measuring the heat that is emitted through the back of the sample. So you have your detector mounted accordingly. On the right, we see a typical graph that you would get from doing an LFA analysis. And from that, we can calculate the diffusivity, which I've noted as alpha. D squared is to do with the geometry of the disk. And T half is half the time it takes for the heat to decay. So there's a relationship with how much heat your sample is able to diffuse and how quickly it's able to reach that T half variable. And from there, we can actually calculate the thermal conductivity if we know the specific heat capacity of the material, which can be measured either through LFA or differential scanning calorimetry, or you could use regular calorimetry if you want. So it's just noted by a function of temperature of the diffusivity, the heat capacity, and then rho is the density of the material. Now, Arya had already talked about TPS, so I'll kind of just go over this slide quickly. Of course, here we've got a sensor that acts as a heat source itself. We don't have to worry about mounting a heat source. It does not come into thermal equilibrium. We just have to make sure our samples are sufficiently larger than the geometry of the sensor itself. And we get these delta T over time curves. In the TPS method, of course, the operator has to be aware of how to change the parameters of their experiment. So they have to adjust the power and the time the experiment runs. But there's built in a lot of checks to sort of help them along the way. So it's a very robust method and it's very quick. So from, again, a user's perspective, when we are chemists, when we do a test, we want it to be as reliable, as high precision as possible. And just to compare LFA with TPS. Again, we have a 15-year history for the LFA before we switched to the Trident. In terms of sample preparation, LFA I classify as moderate to difficult. And this is a mold, so you get pretty good repeatability once you have molds that work and are to the right dimensions, but you also have to make them optically opaque. So that's another step along with sanding to get them nice and smooth. So we have had tests fail because they simply were too transparent. So that's just another variable that you have to consider. With TPS, once you have your molds, you have to sand them to get them nice and flat, but that's about it. So I'd say that's a moderate to easy sample preparation. Analysis time, LFA, you're running 30 to 60 minutes towards the end. And again, we had that instrument for about 15 years. I'd say 60 minutes was more the over under, just because we would have little things, especially with the detector as it ages. It really requires a lot more monitoring. TPS, 5 minutes. Once you know what you're doing, it's a very quick method. Consumable supplemental accessories, LFA, yes, we need a water pump because to reach a thermal equilibrium, we not only need heat, but we need a way to cool it to keep it within a very tight temperature confine. So we need to constantly change out the water source with that. It also requires liquid nitrogen for the detector. With the TPS, we have none of that. Simply plug in your sensor, let it come and warm up for a few minutes, and then you're pretty much ready to go. The LFA noisy, yes. That's mainly the furnace that's running along with the water pump. The TPS, you really don't hear a thing. Robust software, not really, but again, that was an older instrument, so I'm sure they've made iterations since then to make it a bit more user-friendly. But I know for us, we had basically two programs, one that would take the measurement, and then another one that would run it through different models in order to get your thermal conductivity. So your standard operating procedure was 30 to 35 steps long. It was quite wasn't very robust, we'll say. Whereas TPS is sort of built into the software. It's color coded, so it's with minimal practice, you can get quite good at it quite quickly. Footprint, LFA is modest. It would take about half of a standard laboratory bench when you account for all the equipment. It's also quite heavy. TPS, no, you can do this on a standard desk, really. It's quite compact and convenient, as well as it's portable, whereas the LFA, due to its size, its weight, and all the additional things that you need to run it, is not very portable. So you're very much tethered to a workstation. And then finally, if we compare, so here we took a thermally conductive material, sorry about that. And we just compared the two methods. Looking at the data, if we run a two-tailed student t-test, we end up with a very high p-value, much greater than the 0.05 threshold that was typically used. So we can conclude that there's no real statistically significant difference between the measurements using the two methods. So we're very confident that our transition to the TPS method has not in any way compromised the data that we have. So that's all I have to say. I'm going to now pass it back to Aria, who has an outro.
Awesome. Thank you very much, Michael. Yeah, folks, so just to kind of get things to wrap things up here before we go to the Q&A, I'm just gonna bring these outro slides up on screen. Yeah, so just, again, some kind of housekeeping items on our way out here today. So if this type of content, was interesting, you maybe want to take a look at what else we have just, pre-saved on the website. All of the past webinars are available there. I actually just noticed this is the one that was with Michael there about a year ago. So all of those webinars, the tech libraries, everything like papers, you can find downloads to that. I will make note of some upcoming webinars. We actually have quite a busy October here. We actually have 3 upcoming with various guest speakers. Michael kicked us off here. But then in October 14th, we're joined by ARDL, where it will be a focus on thermal management of tires. About middle end of the month on the 21st, joined by some researchers from Penn that will be looking at thermal conductivity of thermal mass and emission saving for buildings. And then towards the very end, on October 30th, we're actually going to have a DMA-focused webinar with Dr. Richard Pazur joining us, Department of National Defense. So an extensive lineup coming through for the rest of the month. So stay tuned and definitely register for those if that's of interest. In terms of upcoming events, I just had the one here, and it's actually happening right now. We've got some colleagues down at the Battery Show North America. This is being held in Detroit, Michigan. So if you happen to be in the area or you are planning to catch some of the content at the shows over the next couple days, the team from C-Therm is down there. We'd be happy to connect in person if that's of interest. But if this was, generally interesting, maybe again, though, you had some more specific questions on how it would apply to your research or some more, application specific questions, we offer technical consultations free of charge. It would give you the opportunity to meet with us one-on-one, discuss again what your needs are, how thermal conductivity is playing a role, and we can basically walk you through, all of that work, what it would take to get set up with an instrument, or again, potentially look at contract testing services. But all that being said, if you're also just looking for some budgetary information, certainly feel free to let us know. Again, my colleague Anga putting some links in the chat there. But if you do just want to get a quote, kind of get some estimates going for an instrument, happy to assist. I will make note that if you are coming and joining from the academic side of things, researching at a university, we do offer an academic support program. I won't kind of read it all out, but you kind of see some of the top line items there. I mean, a flat 20% discount off the Trident thermal conductivity instrument, as well as some other nice benefits there throughout. So if, again, maybe you're looking to bring this into a academic research setting, where we always love to support that side of the business. So definitely feel free to, once again, just reach out with any questions. If you're looking to stay up to date with us with, the latest and greatest in terms of content, events, where we'll be, what's going on, we always post on LinkedIn first. So if you're not already doing so, please give us a follow on LinkedIn. That'll definitely give us the best way to keep connected with you folks. And then, yeah, brings us to the end. So, again, we're going to go into a little bit of a Q&A here for the last few minutes. For those of you that are sticking around, please feel free to do so. I'm going to go ahead and stop the official session here, but then we'll go into that. And for the folks that need to jump off and leave at this point, from myself, thank you for joining us here today. And I'll extend also my thanks to Michael for taking us through that content. So all that said, if you're dropping off, it was great to see you. And for those that are interested in sticking around for the Q&A, we'll jump into that right now.